Thank you very much. Good afternoon, everyone. My name is Felice. I am doing an AEngD with the Centre for Non-Destructive Evaluation, Rolls-Royce plc and the University of Bristol. So let's get cracking. The problem is that a lot of engineering structures already have got cracking, and that's what I'm here to talk to you about today. So non-destructive evaluation is the use of techniques like ultrasonics and radiography to check engineering systems and structures to ensure that they are still structurally sound and safe. A multitude of components are checked every day. These include aircraft engines, which is what I work on, and civil engineering structures, like the Clifton Suspension Bridge in Bristol, pictured here. On the right is an image of someone performing an ultrasonic inspection in this same bridge. The type of cracking that I'm interested in is stress corrosion cracking. As this rather amusing poem says, stress corrosion cracking is an unwanted tree. This is because it is multifaceted in shape, and it can grow unpredictably and quickly, and cause catastrophic failure. Importantly, it continues to puzzle scientists and engineers. It's a problem in the aerospace industry, an extremely common problem in the civil nuclear industry, and a more day-to-day example is pictured here. What sometimes happens in indoor swimming pools is that the chlorine-rich vapor can attack stainless steel components, causing the roof of the building to collapse. So the technique, the NDE technique that I'm working on, is ultrasonic testing. In this technique, we use piezoelectric crystals to send ultrasound into components. And if any defects are present, we receive a signal from them using the same crystal. Ultrasonic testing is used on many materials and components, including nowadays on carbon fiber composites. Some advantages of the technique are that, unlike things like radiography, it's inherently safe. It can be used to find defects that are subsurface, and the equipment can be very portable. So we say that we can use it to perform in-situ inspections. So for example, in the aero industry, you can check aircraft engine components without disassembling the engines, saving lots of time and money. So what about using ultrasound to check for stress corrosion cracking? Well, the problem is that because the cracks are complex and have many branches, using a single crystal means that the ultrasound that's scattered by the many branches will not all reach back to the transducer, meaning that you can miss some of the cracks. Therefore, I'm designing an ultrasonic array. So an ultrasonic array consists of many piezoelectric transducers. They're housed together in the same probe, and this probe can still be very small, so in-situ inspections are still possible. However, the different transducers can be fired individually so that you can focus and sweep the beam at different angles, increasing your chance of finding defects. Furthermore, what we can do is combine time signals and process them to obtain images, meaning that the data analysis is easier to be done. So as you can imagine, when designing an array, there are many different parameters that you need to set. Therefore, my role as an AEngD is to develop a computer optimization tool so that arrays can be designed quickly and at the lowest cost. This avoids the need of having to buy many arrays to try out, and also reduces the time it takes to develop them. So what I have done here is transfer an efficient finite element analysis technique, which was developed at the University of Bristol, into industry. And this modeling technique simulates how ultrasound is reflected by cracks. Now, a common practice when doing ultrasonic simulations is to assume that cracks are slot-like and input very simple shapes into your model. This is similar to the joke about engineers calculating the volumes of camels by assuming they are spherical. Actually, for most cracks, it's fine to assume that they are rectangular in shape. However, for stress corrosion cracks, as an example shown in the background of my slides, this is inadequate because the cracks actually have very complex shapes. Therefore, I've taken a novel step forward and extracted real crack shapes to input into the model. So I have done this by performing X-ray computed tomography on parts that are known to have cracks in them, then conducted what we call X-ray segmentation and image processing to extract the shape of the crack. So as you can imagine, this means that my model outputs much more realistic results. This means that the best possible ultrasonic inspection can be designed for a particular type of cracking. And also it means that we will understand how this inspection will perform before we have implemented it. The two main benefits of this are, firstly and most importantly, that we will be able to find smaller cracks and more cracks, and this will increase the already outstanding safety record of the airline industry. Secondly, because the inspection will be more reliable, we can carry it out less frequently. This saves cost and disruption for airlines and passengers. And this also means that very expensive engineering components can spend more of their lives actually being used. So how does all this fit into the bigger picture? In just over 100 years, flying has become something we thought impossible to something we do regularly without even thinking about. In fact, we are so comfortable with the concept of flying that we sit in planes and have other things to moan about. This is only possible, though, because engineers have designed modern aircraft and engines. It is also possible because engineers work continuously while airplanes are in use. They monitor flight data, and they design and implement maintenance and inspection procedures. So my work will contribute to this because my role is to design customized and optimized engine inspections. My work will also contribute to making this engineering even more unseen. It might seem unsatisfying to work in a job where the better you do your job, the more unnoticed you are, and indeed, if you do your job as best as you can, then no one will even know you're there. However, the very fact that in the modern world flying has become so important is satisfaction enough for me and the people I work with. So these are just two personal examples on why and how flying is so important. So flying enabled me to spend my first Christmas with family abroad. And earlier this month, flying enabled me to attend a one-day meeting in Switzerland. And every day there are millions of examples of how flying keeps families together and businesses communicating better. And our work in NDE is to make this safer and smoother. So I will end with a question which many people ask me, which is, are you more or less scared of flying now that you work in the industry? And my answer to that is not only am I less scared, I'm also much more appreciative of all the work that goes on. Thank you.